Hi everyone, I'm Kwangjun. I'll be talking about work, how to escape sharp minima with random perturbations. This joint work with my two PhD advisors, Jadbabaie and Suvrit Sra. In modern machine learning and AI, models are often over-parameterized, which means that the training loss has multiple minima. So here the central question is, which minimum leads to a good generalization or a good model? One promising candidate to tackle this question is flat minima, extensively studied in the literature and is gaining a resurgence of interest due to recent success of flat minima optimization, such as sharpness-aware minimization. So I'll talk about all of this throughout the presentation. Motivated by this, the main scope of this work is to propose a clear definition of flat minima and study the upper complexity bounds of finding them theoretically. Okay, so let's discuss how we define flat minima. A little mathematical notation here. Let's say f that goes from d-dimensional Euclidean space, where d is the number of parameter, to a scalar, be the training loss. One popular metric for measuring flatness in the literature is the trace of Hessian of f, because lower trace values intuitively suggest flatter regions. And also, it's shown to be quite promising across different works in the literature. To start with, Liu et al. From last year ICML observed that for language models, perplexity, the training loss, is not a good measure for the downstream performance, but actually the trace of Hessian has a better explanation power. So here's the plot from their paper. So on the left side, they're plotting the correlation plot between the downstream accuracy and pre-training loss across various size models. And you see that there's not a good correlation going on. But on the right side, when they plot, reorder this in terms of the trace of Hessian, better correlation shows. In particular, lower trace of Hessian, in other words, the flatter minimum, leads to better downstream accuracy. There are other works in the literature that shows the effectiveness of the trace of Hessian. Another work by Damien et al. From NeurIPS 2021 empirically observed that lower trace of Hessian value leads to better generalization for image classification like CFR10, where they measured the trace of Hessian value across a training trajectory and noticed that trace of Hessian value goes down, and that leads to better test accuracy. There are more theoretical evidence. Several work have shown that better generalization can be rigorously proved for specialized models, such as low-rank matrix recovery over-parameterized, so it's a non-convex problem, or deep linear networks, shown by this two works, Myanin and Gamiri et al. From last year. Also, notably, several works have shown that practical optimization algorithms have implicit bias to reduce the trace of Hessian, such as SGD with labeled noise and SAM. So motivated by all this success of trace of Hessian, in this work, we adopt a trace of Hessian as the metric of measuring the flat minima. So here, one thing is, since trace is the sum of D terms, in order to put it on the same scale as a training loss, let's consider the normalized trace of Hessian, where we just simply divide the trace value by the number of parameter D. Okay, so this will be our main focus throughout our work. And given this, our definition of flat minima intuitively, or in words, is that a local minimum of training loss for which one cannot locally decrease this normalized trace value without increasing the cost training loss. So this concept becomes non-trivial when the set of local minima is connected, which is the case for over-parameterized models. And let me illustrate this through some examples. Before that, some of you guys might think maybe more intuitive definition here is to consider a local minima, which is also local minimum of normalized trace. But this definition is not quite well defined because the set of local minima of training loss can be disjoint from that of the normalized trace. Okay, let me give you one example. Consider this very simple non-convex two-dimensional function that maps x1, x2 to x1, x2 minus 1 to the square. Then the set of minima clearly is this parabola defined by x1 times x2 equal to 1. And with some calculation, you can show that normalized trace is nothing but x1 squared plus x2 squared. So you can see that the unique minimum of this normalized trace is at the origin, which does not intersect with x star. So this first attempt, the intuitive definition is not quite well defined here. So instead, our definition considers when restricted to the set of local minima x star, the normalized trace value achieves its minimum at 1.1 and minus 1.1. So we call these 2 points flat minima. Put it differently, we consider the local optimality of the trace value restricted to the set of the local minima x star. Right. So let's make this more formal mathematical definition. So as an initial effort, our goal in this paper is to find the local minima that is also a stationary point of normalized trace with respect to, so restricted to the x star, the set of local minimizers. Okay. In order to formalize this, we need to introduce one technical definition, namely the limit point under gradient flow, extensively used in the previous theoretical works like Li et al., Aurora et al., and Wen et al. So what it is basically given a point x, phi x is the limiting point of the gradient flow on the training loss starting at x. So more formally, if xt is the iterate of the gradient flow starting at x at time t, namely this solution of this ODE, then phi x is defined as the limiting point of this gradient flow. For the purpose of this presentation, you can just kind of regard phi map as follows, where phi maps each point x to its closest local minimum. So it's kind of like a projecting operator that maps each point to the closest local minimum. So that's the intuition behind the limiting point under gradient flow. Then with that, we define flat local minima as follows. We say a point x is a flat local minima if it's a local minima and satisfies this equation. So basically, if you're restricting the normalized trace onto on the x star, the gradient vanishes. Precisely what we're looking for. Another intuition here is that if this gradient value is non-zero, moving along the negative direction of that gradient will locally decrease the value of this trace of phi x, so restricted to the x star, while remaining in x star. So you can reach flatter local minima if this gradient value was not equal to 0. So hence for flat minima, we want this gradient value to be 0. So in order to talk about the complexity, let's define an approximate version of this, where we call epsilon prime flat local minima. We say point x is an epsilon comma epsilon prime flat local minima if x star, which is the nearest local minima of x, it satisfies that x stays close to its nearest local minima x star, and also the gradient that we just discussed, the gradient value is not too large, so bounded by epsilon prime. Sorry. So in other words, 0,0 approximate flat local minimum is a flat local minima. So given this, our main results can be stated as follows. So depending on settings, we study the iteration complexity for finding epsilon comma square root epsilon flat minima. So our first main result says that for generic training loss setting, we can find such flat minima within epsilon to the -3 gradient queries using algorithm randomly smooth perturbation, which I'm going to describe shortly. And for specific case of training loss, where it's a form of empirical risk minimization, then we can actually do better by doing more like a sharpness-aware minimization technique, which we call sharpness-aware perturbation, and we're going to discuss this also shortly. Before that, let me just state the set of assumptions that we employ in our analysis. So for this flat minima to be well-defined, you can imagine that f has to be sufficiently smooth. In particular, we assume that training loss is 4 times continuously differentiable near the set of local minima x star. More formally, within a small neighborhood of x star, we assume that f is 4 times continuously differentiable, and the limit map under gradient flow phi I described earlier is well-defined and twice continuously differentiable, and locally PL inequality condition holds. In fact, the last 2 conditions are actually consequences of f being 4 times continuously differentiable due to results from Arora et al. 2022. But just for concreteness, we added them in the assumption. So let me move on to what our algorithm looks like. First algorithm for generic training loss is called randomly smooth perturbation. And the description I'm going to provide for this slide and the following slide is informal, and the actual algorithm has some technical components. So for details, please see our paper. So roughly speaking, randomly smooth perturbation algorithm does run GD until it reaches O epsilon neighborhood of the X star. And then we switch to the following update rule, where instead of following the negative direction of the gradient, we actually follow the negative direction of the gradient computed at xt plus rho. Rho is a perturbation radius times gt, where gt is just a random unit vector. For those who are familiar, this is nothing but randomized smoothing, the popular technique discussed in Duce et al. From 2012, and has been extensively used in non-smooth optimization over the last decade. And our main results show that this kind of randomized smoothing operation actually leads to flatter minima, hence showing unexpected benefits of randomized smoothing. Okay, moving on to the second algorithm that we consider in the paper. This algorithm works for the training loss setting, where let's say n is the number of training data, and PIX be the model prediction output on the ith data, and YI be the ith label. Then the training loss is just this ERM form, where it's this average of summation over FIX, where FIX is defined as PIL, some loss of choice of PIX, comma YI. Okay, under this training loss assumption, we consider this sharpness-aware perturbation algorithm, where we run gradient descent again until it reaches the small neighborhood of X star, and we switch to the following updates, where now we consider the stochastic gradients Fi at the points that's perturbed by the stochastic gradient direction. Actually, it's a stochastic gradient ascent. So this is precisely like the technique considered in the SAM paper. And our main results says that this SAM-like operation, or more specifically sharpness-aware perturbation, finds flat minima faster, as we described earlier. Okay, so let me conclude this talk with some summary and future directions. We all know that in optimization for machine learning literature, over the last decade or so, there has been great success in theoretical studies on the question of finding approximate stationary points, evidenced by all these works from the literature. And this work extends this line of research to a new notion of stationary point motivated by the practical success of flat minima optimization. We call this approximate flat minima. Future directions are include obviously further studies on defining and refining the practical notion of flat minima that parallels practical success. We chose a trace of Hessian motivated by all this theoretical and empirical works, but there could be some better measure of flatness. And then under that new notion, designing efficient algorithms for them. And also, whenever we're talking about complexity, characterizing lower bounds are important, as done in the realm of finding stationary points, evidenced by all these great works. Thank you for listening. And if you have a question, feel free to shoot me an email. Thank you.